Okay, thank you very much, Marco, to invite me here. You know, and thank you everybody for coming here. And you will see that, in fact, that's for my English is bad, you know. So I will read and speak in English, things that you can read yourself. You know, it's more, it's not so well, you know, I don't understand. Maybe it works like that. I'll speak and present some informations, maybe you know, maybe not completely, about Cavalieri, the mathematician and the producer of the theories, indivisibles theories as method. And some information before, not any story of indivisibles, like 1 or 2 points before, and some information about the reception. And the reception until the end of the 17th in Keck Center. So just very briefly, they were front and original impossibility. In the 5th century before Christmas, with Zeno's paradox, thinking rationality about motions seems an insurmountable task due to infinite arguments. Shortly later, Aristotle built a consistent argument defending the continuous is not composed of indivisibles, which are paradoxical objects. This hasn't put an end to the controversy, and throughout history, we have come across authors who maintain the actual existence of infinity and the composition of the continuous by indivisibles. We can mention Mujahid in Islam in the 18th century, the medieval atomists Henry of Ackley, Walter Sharton in the 14th century, and in geometry, methods are developed to get around or deal with infinity. We are thinking of the exhaustions method employed by Euclid and Archimedes, among others. An episode I am very interested in, but I will speak briefly, related to our question, take place in the late Middle Age, 3rd and 14th, mainly 14th century. It concerns 2 main centers, Merton College in Oxford, created by Robert Grosstedt, Paolo Mancosu told days ago about that. And the second place was the University of Paris with Jean Buridan, rector of the university, and Nicole Oren. Sometimes they are known as the physicists, Parisian physicists, you know. Pierre Diem talked about them on the predecessor, Galileo predecessor. And I think it's not it's reasonable. The aim for this thinker, they are a philosopher, mainly interested in mathematics and geometry, but mainly as philosopher, you know. And the question was, can qualities be quantified? And how? Qualities hot, cold, wet, dry, but also color, virtues, you know, courage, kindness, etc. Things like that. Can we measure that, evaluate it, compare this? Okay? And maybe I focus on the most interesting for our talk is the speed. These qualities are subject to intensity. One soldier could have an intensity more than another one, and comparison and reason, but not to addition. How is a quality measured if not by addition? And we have, for example, 3 examples. A metal bar is heated. At every point of the bar, the heat has a certain intensity of this quality at each point. So it could be, each point concept of local concept, you know. Someone sense his virtue. Every day or instant of his life, his virtue has a certain intensity every day or every hour, I don't know, every week, I don't know, every point or day. But, you know, it's a certain intensity. We can say, oh, this week is more, virtue more. An athlete runs fast, I hope, for him. At every moment or place, you know, of the run along the way, his speed has a certain intensity. And the vocabulary is, for instance, in the case of the speed, the degree of, say, gradus velocitatis. Gradus velocitatis. What about all these degrees of intensity taken together? Comes the question, you know. All along the bar, all along some life, all along the course. You know. How can we build something or something about that? You know. And in Horace's famous book, we have what we say Horace's configuration. We are in the 14th century, you know. It's a remarkable idea of this 14th century theorist was to seek out geometrical representation of this changing intensity and of their taken as a whole, you know. The first ones are represented by straight line, the intentiones, a segment, you know. And it's what Rosie Bacon, for instance. And you have a lot of styles of manners of being taken together. Then considering the extremities of the segment that express the intention at each point, we can deduce a line that gives a surface, right? Thanks to that line, straight or curved, the intentionless degrees of quality can be considered together. That an area is thus defined that measures the overall quantity, perfectio virtus in vocabulary, orisons, or total heat, velocitas totalis, speed or force of the accomplished movement. For instance, this vocabulary of the vis motu, the force of the movement, is used by Descartes when many years when he tried to use the indivisibles to study about the or falling bodies, you know. And he takes the triangle he obtained, design that has the force du mouvement, vis motus. And in his questiones, Horace writes, the quality at a point, that is an indivisible subject, must be imagined as a line. It has only one dimension, intensio, which is way on increasing. The way in which certain intensive quantities could change, therefore, suggested plain geometrical representation. If in the case of a rectangle, we have a variation uniform, a modus uniformitaire. Okay. No variation. Not a variation. Sorry, it's not correct, you know. It's in the first time, it's uniformitaire, no variation. In the second case, you have a variation, uniform variation. You produce a triangle, you know. And like an irregular plane figure in the case of irregular, deformement deformed, you know. And we obtain some result. For instance, is that we have the theorem, thanks to these representations, and we have this theorem of the mean degree. You understand?
Vincent, if you point on the screen, we do not understand what you point.
Okay.
So you have to point there. And you should also use this one to count.
Yeah, the theorem of the mean degree, telling that all the speed is the same if it is time variance. All the speed, V's motus, is the same in the case of no variation movement, always the same, or if a variation is the uniformément varié, but with the n is the double of the degree of the situation, no variation. And that this theorem, you have explaining that the variations are minimal at the extremum. Okay, so of course, if you think about the concept of indivisible, you can see that we are inside. This is open. Among these quantities, the velocity of a moving body was of particular interest. The intensio could be the time or the space. And probably you know that the discussion included in Galileo, included in Descartes. For instance, Galileo at the beginning, the first text about the result of the law of the movement, Galileo takes as intention, intensio, we can say, he takes the space, not the time. It was a few years later that it changed and take the time, and took the time. Neither for Oxfordian nor Parisian, it had been linked to the actual physical phenomenon of a falling body. All that are consideration completely abstract, for them. Consideration about is it possible to have a concept to evaluate the qualities, but it's not for building a physical, nothing like that. In an absolutely general way, the measure of ratio of two linear qualities or qualities or any surface is equal to that of the figure by which we represent them in a comparable way. And in the case of local motion, the subject is linear time. The intensity of each point of time is a line. The linear quality associated with time is a surface that Horace called total velocitas. It was generated by degrees represented by segment perpendicular to the subject, degrees proportional to intensity, etc. We must speak in the same way of the measurement of a speed, but taking the time during which this speed lasts, for the extension and the degree of speed for the intensity in the trifecta. By virtue of this transposition, the theorem of uniformiter deformis latitude became the law of traveled space in the case of uniformly variant motion. The demonstration can be likened to that of Galileo. In fact, this law was never forgotten in the interval between Horace to Galileo, as it was taught in Oxford by William Aylesbury and his disciples, and in Paris and Italy by all the school's subsequent disciples. In the middle of the 16th century, long before Galileo, the Dominican Domingo de Soto applied this law to the uniformly accelerating force or heavy body and the uniformly decreasing ascent of projectiles. Clearly, we have a source for the indivisible. Another inspiration plays an important role during the 16th century. We can talk about the standardization or Archimedean, we say Archimedean or Archimedean production. We can mention Simon Stevin and Lucas Valerio. We owe them a deliberate, systematic effort to simplify the structure of Archimedean demonstration. I don't know if use the word simplify is a good word. Simon Stevin treats the final stage of the double reduction as a general routine of standard argument. The words are not completely correct because in Archimedean demonstration, you have not a final stage. You have two steps, one analytic, another synthetic. The first to discover by method of indivisible, we can say that, the result. And the second one is to produce a demonstration, rigorous demonstration, that this result, suppose the real result can be superior and be inferior to is equal. So in this second argument, who in the tradition is produced for every case, Valerio and Stevin explain, okay, it's an argument, a general argument, we don't have to produce it each case, okay? Luca Valerio adopts the same attitude and obtains beautiful quadrature with that. So, we'll be meeting various definitions with Cavalieri or characterizations of geometrical indivisibles. Maybe the main difference between heterogeneous in Cavalieri or Galileo and in some text by Descartes and others, or homogeneous in most of the authors engaged in the field. There are other characteristics, but maybe this one is maybe principal. Homogeneous if they are of the same dimension as what they measure, line for measuring line, surface to measure surfaces, etc., or volume to measure, etc. And homogeneous, homogeneous if they are at the same dimension as what they measure, otherwise heterogeneous. So line for to measure area, it's heterogeneous. Enrico Giusti, an Italian scholar, proposed a clear thesis that indivisibles do not acquire a true objective existence, even in as mathematical objects. These objects are unable to crystallize and remain, so to speak, below being stopping at the stage of research instrument or demonstration method or object of study without ever taking the final step toward an autonomous existence. For him, the indivisibles are, that is my impression, my interpretation. The indivisibles are like a false stray or maybe a sidetrack, une voie de garage. Okay. I propose a different assessment, recognizing the contribution of this object and method, indivisibles, to a wider program that will culminate in the integral calculus. If you want, I think more that indivisibles method and works took part of this general construction. The origin of indivisibles method is the controlled and mastered use of infinitesimal procedures in geometry. Of course, the various methods do not complete this part, but they do constitute a fruitful stage in it, and not a wrong way. The common achievement with the introduction with a view to clearly identify realization of a non-Archimedean geometric quantity, that is the nucleus. These are quantities whose summation, be it repeated ad infinitum, does not exceed a given magnitude. This is obviously the case with point for straight lines, instant for duration, but as we shall see, for other kinds of objects designed for this purpose, homogeneous indivisibles. So, let's go to Cavalieri. Oh. He took the name of Buonaventura when he joined the Jesuit. It's not the Jesuit, it's not a it's a different order, coming from the Franciscans, not descendants of Jesus. When he joined the Jesuits in Milan, 1615, and was appointed as professor to Pisa in 1660. He was introduced to Galileo, whose disciple he now considered himself. Galileo wrote of him, few perhaps known, since Archimedes have gone so far and so deeply into geometrical science. He published his Geometria indivisibilibus continuorum nova quadratione promota. Well, the important in this long title is not Geometria des indivisibles, Geometria continuorum nova quadratione promota in 1635. He concentrated his research on infinitesimal questions. It's difficult to follow the author through the almost 700 pages of his book. Some say that his style is very, very hard to complicate, not very clear, but nevertheless, he was reprinted in 1653, and Cavalieri published a second book on the subject, Exercitationes. Cavalieri's conception of what are indivisibles, well informed about philosophical consideration concerning the possibility or impossibility of forming continuous quantities from indivisible ones, Cavalieri set out to form a valid method, whatever the answer to the speculation. He wanted to produce something independent, who works. Whereas Galileo wrote, for instance, I quote, the ultimate and supreme and yet the first components of the continuous are the indivisible infinities. Cavalieri answered the wrote in June 30, I dare not affirm that the continuous is composed of indivisibles elements in a letter to Galileo. It's a story. Now I don't know. The relations were good, but they know Galileo and Cavalieri knew very well that they were not in according, So the definition, we can say one, the definition one of book 2, can read it, if true either, if I read it, more confusing. So you have a plane or all, I don't know what, to produce indivisible in a plane, he has to have two planes descending, a plane descending. Maybe we can say, okay, descending from the top to the bottom, and at each instant point or situation, he produced lines, okay, in the first and in the second, and these lines produced are the indivisibles of these two figures. L for the figure F, L prime for F prime, okay? And the single part of straight line, which in all these movements are the intersection of the moving plane and the given figure, gathered together are called, by me, Galileo, all the line. He's not the first. Remember Horizon proposed to the same vocabulary, all the intensio. Yeah, all the line of such a figure. One of them being taken as regular. The regular is designing the direction. Okay. Nor does it affirm or deny the actual or potential existence of indivisibles. Their nature remains a work of mystery. And I quote this passage, for me, is very impressive. I've used about the object he built, for to build a new geometry. I used an artificial similar, it's interesting the comparison. Similar to that often used by algebraists for solving problems. For, however, ineffable, absurd, unknown, the roots of numbers, so it is the same for with my indivisibles, Okay? They nonetheless add, subtract, multiply, and divide them. And they are convinced of having sufficiently met their obligation when they have succeeded in finding out from the given problem the result which was required. No differently, therefore, is legitimate for me to make use, in order to investigate means of continua of the aggregates of indivisibles, either offline or plane, for if are nameless, absurd, unknown with respect to the number, their magnitude is enclosed in well-defined limits. Okay. And Egidio Festa, which is an Italian, Franco-Italian colleagues, okay. Cavalieri asserts only that between continuous quantities there is no other proportion than that of aggregates of their indivisibles. The aggregate contains, that is Festa, using the word contains, all the indivisible of a given geometric quantity taken together.
When here it says the roots of numbers, does it refer to roots like the root of number 2 or the imaginary roots?
Yeah.
Like the root of -1?
Yeah, of course, yes.
Yes.
That is the point. Yeah. And in the definition, maybe not the more important, I don't know if it's more important, but the more controversial concept is the omnes, all the taken together. In Geometria, so all the lines of rectilinear transit of any plane figure and all the planes of any solids are magnitudes that are proportional to each other. The same about the plane. If you have a solid and we have individual plane, okay, all the plane, if given any solid, two opposite tangent planes are conducted arbitrarily and indefinitely extended. So if it is the same for a solid, but the indivisibles are plane. Okay? And all this gathered together are called all the planes, or the given solid, taking as direction one of them. The quantity omnes is thought of as an Euclidean or Archimedean quantity. It is capable of reason. It is also subject to addition and order. The quantity omnes is distinct from the magnitude figure itself. For Galileo, there are 3 steps here. You have the indivisible, you have all the indivisibles, you have the figure. And the point is that if in 2 figures we know the proportion, ratio between all the indivisible of one to the other, it's the same for the figures themselves. Right? And the quantity is so but the quantity of omnes is distinct. It can be observed that nor in the interpretation in terms of sum, neither in terms of set, is actually unclearly relevant to understand the omnes indivisibility notion. Of course, Galileo knows that if he says it's just a sum of line is a line, okay. And if it's a set, he meets the difficulties between the number of, in figure difference, you can have the same bijections between the elements. So, omnes degrees of speed, is important. The area measures the velocitas totalis, the same thing we did, but more important, it's different in that situation because it is necessarily connected with the work, physical work about the real move, falling body, for instance. You can say, it's only. This applies in particular to indivisible relating to local motion and velocity. On this point, we can associate Cavalieri with his master Galileo. According to Egidio Festa, the total velocity of a moving body was thus conceived as the juxtaposition, that is Festa vocabulary, of an indefinite number of grads. The intensive magnitude, in this case total velocity, velocitas totalis, is all the gradius velocitatis taken together. See, all right. Neither Cavalieri nor Galileo ever really clarified this aspect of the problem. For them, the juxtaposition of gradius velocitatis naturally gave rise to the velocitas totalis for the move and the body. I showed to Tommaso when we had no time. Cavalieri produced an original figure about velocitas totalis. Of course, he knows as everybody, but he produced something else. He was very proud of that. He said, in a point, that is the vitesse null, okay? And for the vitesse growing, I choose to say circles, and the circles are growing. And he said, and naturally, if I want to see, to have the total speed of the move when it's finished, it is the area of the disk, of all that. So the indivisibles here are the circles. So it's difficult to understand why he wanted, because like if for him it would be more natural to say, okay, to measure all these circles. This is the first of the circle. I don't know, but he didn't do why this is better than that to convince us. All the omnes, all the square, etc. Look at that. For instance, Cavalieri will produce a general concept of omnes, all the à partir from a certain figure, we produce different things. Given any plane figure, if you can read, it's better than anything to read. And if any straight line having its extremity, for instance, with tools, points as tools, right. We can say, we have this figure, of course, you have these indivisibles, the lines, okay. But we can, with each line, each indivisible, you can produce a square, for instance. Or maybe not a square. It could be a disk. It could be something, but it could be a triangle. But all the figure you produce for every line has to be the same, similar. And so we understand clearly you have, thanks to this figure, the quantity, all the square, all the triangle, all the so. And for another example here, like complete, if we have a line O and a segment ON, you can produce, of course, all the points, but on each point you can produce all the the abscess, all the abscess. It is for each point here. You have here, for example, the distance from O, and you can do that. So you produce it's another manner to produce a triangle, but from a line you can produce all the abscesses. And some said, here we have something like we can recognize for the future, the integration of X. It's not correct if they put something like ON X dx, but it's interpretation. So the important is to understand that he produced very much rich family of but mathematically is very very chronophage, you know. I'm not, you know, this is all this discussion, all this demonstration will take time. But in Cavalieri is one point very interesting, that his concept, for instance, in all the square, or, you know, and on these indivisibles in general, all the, he connect it with some calculations, you know. For instance, here we have this parallelogram, this program cut into the two manners to be cut into the diagonal by this, okay? And so you have a big parallelogram, two big triangles, two small triangles, okay, and two small parallelograms, okay? And he had we can say geometrical algebraic relation if you want. Imagine the line RS is going down, okay, like that, okay, from AC to EG. At each point, you have an expression like RSTV, and you can look at that. That is elementary, evidently, of course. You have this situation: AT squared with TV squared is equal to this. And then he did, let's go to all the square of this figure. You imagine all the square. So he produced all the square of the RBFE. Imagine it's a prism, okay? Mm-hmm. Imagine all the square of BCN. It's a small prism of a pyramid, okay? Mm-hmm. You have another one, a small one here, and a big one here, and a big one here, okay? You know, when you say all the RT, it is all the square you can imagine in this figure, okay? It's clear for you, no. Or maybe all if you have all the ST, yeah, all the here, etc. And then he adapted and he used some well-known proportion between similar figure or different with the linear dimension, for instance, the double of the triple. So, and in the book, he talked about the proportion between two, for instance, two prisms, similar but in the proportion, linear proportion of 2, so the prism in general is a proportion of 8, you understand me? So, and then at the end of this very simple group, he says that 3 on this ACE, it is all the square of ACE, it is a pyramid, you know, the 3 of that here is equal to all the square of ACGE. So that it's a demonstration, an automatic demonstration of this result that the pyramid, you know, volume 3 times less than the total prism, okay? That is an example of maybe not, often maybe not of new results, sometimes yes, but you know, the way to produce it. And then, sure. The most sustained criticism comes from the notion of oddness. You know, against this notion is it's not clear, you know. Is it a sum? Not because sum of line is a line. It is a set, not because, etc. The paradox. Can put in music. For the well-known, you know, opponent was the Jesuit mathematician Jullien. He considers this concept absurd. No geometer will ever accept that a surface is and can be called a geometric, in geometric language, on the line of such a figure. Okay? He published books and Cavalieri, in what has been described as the controversy was strong, you know. But Cavalieri in what has been described as the second method. We heard about the first Cavalieri first method, Cavalieri second method. And the second method, he tried to dispense with it in favor of, with the concept of omnes, all the line of the indivisible line, in favor of a principle of indivisibles that Ettore Caruccio, for instance, in this dictionary of scientific biography, summarizes as follows, This principle is to, if you want, if two plane figures are intersected by parallel straight line, and if the chord lines defined by the intersection are equal, then so are the area of the figure. Okay? If the lines are in the constant ratio, then the area are in the same ratio. And similarly for solid. In fact, is to say, I told you that there were three steps in the first method, and it's the second. Or if the lines are equal, or if the lines are in the same, okay, we say that the figure. And on this, we can forget. Bon. Just a personal opinion. I'm not, many of commentators of Cavalieri discuss about the first method, the second method. For me, it's not so important to be, I often, for Cavalieri, it's to stop the controversial situation.
Sorry, I have a simple question.
Yeah.
Why is this method distributive? I mean, I don't understand why this method is distributive. Why is the distributive method?
Yes, it's because we direct use each line, if you want, each line. It's not very clear why it's distributed.
So the question
it's
is
nothing to do with an operation. Everyone.
the distributive. Okay.
Okay. No link.
Okay.
No concerning an operation.
Okay.
So the question is why it is called distributive?
Yes.
Yes.
Well, it's not. It's a question I had sometime, but I never.
Who call it a distributive?
It is it's very common, So, and what means exactly that this line of surface constitutes the figure beyond? That is important point. But is beyond our understanding. That is the conviction, the position of Cavalieri, in fact, But never ceases to be true. This is, in fact, I think, the Cavalieri, we can really analyze this. It's valued to be together. Whether it's Cavalieri's first or second methods, what remains valid is that they carefully avoids recourse to very small quantity or to approximation as precise as desired. In short, to every that the exertion method sought to control. Contrary to frequent belief, Cavalieri doesn't neglect infinitesimally small quantities. He makes no approximation. He omits no term. He breaks, I think, with the exertion method. In Book 7 of Geometria, Cavalieri gives several demonstrations of this principle. Because you can say, yes, but he says just like that without argument to me, Or we can direct produce the passage between lines to figure. And it's just something well known. I will show you in that slide, I have the argument, and the next slide, I have the result. Look at that. Imagine you have two figures A and B satisfying the hypothesis, equal lines. Okay, they have not. By translation, we can superpose the two figures, and they are a part in common. Part of the two figures, if they are not the same figure, they are a part in common. Okay, which we remove from the figure. two figures remain, which also satisfies the hypothesis. By translation, we continue to the superposition, and at each time we look at this. Look at this. Okay, that is the drawing from Cavalieri. You have the two figures, and it's a little bit different. We put this one on this one. All what is in common, you eliminate it, okay? It reste the figure plus petit. Right, okay, and you continue to superpose, okay? And you eliminate what is in common, and you continue, and what say Cavalieri, that by translation, it's impossible for one figure not to be exhausted at a certain point without the other also being exhausted. And Cavalieri concludes that the figures are equivalent. That is the demonstration.
Can you show again the figure? This figure is not clear.
The figure is not clear. Okay. Look at that. Yeah. Maybe that, you see that? What the rest after the superposing the two, Oh. So you don't see that? We can discuss it on that, but because after that,
But I think the general argument is clear.
Yes.
Yeah,
Yes.
put together, throw away a slice.
Yes, but it's not clear for me.
So imagine, Marco, look,
Simple case.
you have these two things,
Yeah.
then you put this together. I mean, superpose one, and then when you superpose
No,
it,
I understand.
right? There's a part that remains and the other parts that remain.
Yeah.
If you keep doing that and subtracting what coincides, and at the end nothing remains in one figure, not the other, then the two are equivalent.
Yes. So
Yeah.
if I suppose this, I will have this and this. I eliminate this one, I
Yeah.
have this and this. Then
Yeah,
I
yeah,
suppose this is the idea.
Yes.
Yeah.
Yes.
Exactly. And you continue. Okay.
I suppose
Yeah.
what I have here, I will have here. I eliminate this one, I
Bravo.
have this and this. I understand.
Bravo, Professor Ponza. Exactly.
So you could have made a better figure.
That's frankly, Marco, that's a picture we use in our book. So,
I actually used it.
yeah, we use this.
Oh my God. I forgot.
Okay. Thank you very much, Marco. And about diffusion and reception, of course, it's very rich, but we can read it.
No.
The artificial intelligence we propose that it's not very good. No, it's a lot of quotation about the reception of that. And I could use the concerns. I agree with him that he said in France and in general in continental Europe, Cavalieri is known directly. We may assert without any doubt that in the following decades, 14, 15, the idea of Cavalieri has become familiar to most of the French geometers, French and other. The Geometria and Indivisibles of Cavalieri achieved popularity almost immediately and become, except from the works of Archimedes, the most quoted source for mathematicians dealing with infinitesimal consideration in geometry. Torricelli, Evangelista Torricelli was a pupil of Cavalieri, but knows so well the Cavalieri's work that he is sometimes, many times, credited with transmitting Cavalieri doctrine, which is interesting because Torricelli has a great reputation, and he has a conception very different from the indivisibles. Torricelli was a promoter of the homogeneous indivisibles. And because of that, some mathematicians who know the methods through Torricelli were convinced of the Cavalieri's method. Bon. Descartes used them sometimes brilliantly, for instance, on the quadrature of the cycloid quadrature, but also during all his work about trying to establishing a law of falling body. Of course, Galileo in the discourse about the fall of body used indivisibles. And I just quote some other mathematicians. Mengoli from Bologna, the pupils of Cavalieri, focused his work on developing the combination of algebra and the indivisibles. That is interesting in Mengoli, its origin for that. And Isaac Barrow, Marco, we have something sure, mentioned geometers who apply the excellent method of the indivisible. Wallis, in the Traité des sections coniques, propositional, mentioned, I quote him, plane figures considered according to the indivisible methods, I suppose to begin with, in accordance with Cavalieri's geometry of indivisibles, that any plane may be considered as formed by the assembly of an infinity of parallel lines. As for myself, this demonstration I have produced following Cavalieri's method of indivisibles are sufficient for me, since I have found it already admitted by geometers, etc., etc. I can publish, back to Pascal, Roberval, Fermat, till Leibniz and Newton. So just to say that it's Comodine vague, it's a wave. I see that like a wave in the geometrical, This author, in general, develop, amplify, and diversify the methods of indivisibles. Even if they always, or almost, for me, it's an important thing, or even if they always, or almost always, call it Cavalieri's method. For Joe, I produce this to figure, just to show you that it's nice to see all the figures on Cavalieri. It's very beautiful. It's very variative, fantastic, So, and from later commentary after one century and a half, Lazare Carnot in Métaphysique du calcul, the great geometers who followed him, Cavalieri, soon grasped the spirit it was to this method of invisible, but that Pascal and Roberval owed the successor of their profound research on the cycloid. Or Montucla, the famous historian of mathematics, wrote, it is from the time of this, the indivisibles method, that we must count the great progress that the science has made and by which it has risen to the state of it is in today. What is terrible is that there's something other things to say. You have different versions, in fact, in the reception. Isaac Barrow, for instance, recognized that language does something disservice to those who apply the excellent method of indivisible. In that way, it seems to be saying that all these parallel lines are equal to such a plane. What has to be understood by these expressions, however, is an infinite or indeterminate sum, not a line, but of parallelograms of a very small or no considerable aid. In taking of planes whose sum is equal to a solid, we must equally understand prism or cylinder of no computable age. We see it tentative to change the concept, And it is not only like Barrow. In Wallis, it is the same maybe situation like that you can read. I would prefer, d'après, would prefer it if any plane could be considered as formed by the assembly of an infinite number of parallelograms. But you know, there are strange parallelograms, as you can see, of the same width, the width of which is equal to of n for l'infini, okay, of the total width. The infinitive is in a small adequate part, etc. So, such that the array of all parallelograms taken together is equal to the width of the figure. And you can, in Wallis, he said, our method begins where Cavalieri's method of indivisible ends. This is the starting point for both the work itself and its title. So, okay. But he continued to use the word, you know, and to recount of the Cavalieri's method. And for Roberval, there are, we say, give two quotations of Roberval. This first is maybe not the most interesting, just right to Torricelli. Let's turn now to indivisibles. They had strong discussion, Torricelli and Roberval, mathematical, geometrical question. Let's turn to indivisibles. Did the illustrious Cavalieri invent them before he did? I know, but he said, I know this 5 years before he invented this doctrine was useful to me in the complete resolution of this difficult proposition. But don't worry, I don't take the invention of such a simple doctrine, etc., etc. So I had a doctrine, so, which is true, you know. But the interesting is not that, you know, because I have a good relation. It's not, but now what would be interesting, what is the difference between the two doctrines? So Justi offers a synthetic of thought, you know. Faced with his novelty, 70s mathematicians fell into two categories, says Justi. On the one, there were those who rejected the principle of Cavalieri theory outright, opposing it with classical methods was regarded as models of canon rigor. The best known is Paul Gildin, the main opponent, etc. On the other hand, there are those who, while finding in Cavalierian theory an important research tool, appreciate above all its flexibility and efficiency, but who remained indifferent to the invitation coming from Cavalieri himself to get deeper into the theoretical apparatus. That is a justice, we feel the justice, there is no real indivisible theory. You know, it is a common tool. It's interesting, this discussion. Paolo Mancoso notes the following, which the analysis of technical objection to the geometry of indivisibles will show that many mathematicians and philosophers endeavor to justify Cavalieri's method theory in terms of homogeneous quantities. You will see that if I take another 10 minutes.
Go.
I try to
Go.
talk. For me, there's one point interesting, that is a surprising unanimity for me. You know, virtually all the Greek mathematicians adopted this terminology. But at the same time, many of them produced a notion of indivisibles as homogeneous, a notion deemed contradictory to the Cavalieri conception. Roberval, Pascal, Wallis, Barrow, Leibniz, and others, you know. This tolerance, you know, or adaptations, and how we say, Mancoso, we say that it is flexibility, you know, the flexibility. We can say three explanations. The two first, okay. The first, you know,
It is not completely clear to me explanation of what.
Yes, it's important because it's my point. It's a quasi complete unanimity, but Gildin and some other we say no way, we doesn't want to use that. Okay? But in all the others, great majority, it's some sort of unanimity to say bravo for the method, indivisibles method. But in many of them, they of course recognize they produce a different concept of indivisibles, you know. And but
So you mean the method was the same, but the interpretation of the method were different.
The point is the method the same. I will try to say this is okay. I follow it. No, the first explanation of this unanimity could be purely formal attitude. I quote that because if at least one historian of math in France, François Guégan, said it's purely formal attitude. A polytome is carelessly rendered. I don't comment, I don't know, it's not the style in the mathematical community, in particular in the 17th century, to say, oh, it is agreeable, we say, yes, it's okay. No, it's mostly competitive. The second explanation is to maintain that people, the geometers, did not understand Cavalieri's proposal and above all did not see the difference between his proposal and what they themselves were working out. For instance, Torricelli or Roberval or Pascal. This is implausible and above all explicitly denied by several of them. Or they wouldn't really have read it. That is the thesis reported by Kirsten Anderson, very good specialist of that. They said, in fact, Cavalieri was very well known, but the major geometers didn't learn indivisible through Cavalieri, but maybe mainly through Torricelli or Roberval or others. But I don't think it's correct. It's very difficult to accept. And the third possibility is that these mathematicians actually read and saw in Cavalieri's invention the indivisibles they themselves were going to use, or at least some of the main characteristic features of what they were inventing. They would not have considered this to be an essential difference. That's the one that seems right to me. I will try to show why I think they understand the difference. But they sincerely thought that this difference is not essential. There is something in common between, for instance, there is something in common between the heterogeneous method, homogeneous method, something in common, which is the most important. Okay? So I continue to visit some. That is, as he finished this. The importance of I say a common nucleus, it's understandable that, and voyou commun, something important. Let's see how this appropriation, which is also a transformation, is claimed. I need two, some quotations here. There is a lot. I quote Bortoletti, writer about the géométrique de Torricelli.
Bortolotti, but
Bortolotti. According to Bortolotti, the Torricelli's point of view is that Cavalieri's indivisibles are not Euclidean lines, but elements of area, and as such, they are comparable not only by their finite length, but by their infinitesimal area. In fact, Cavalieri's indivisibles in Torricelli's conceptions are composed of two factors, a definite factor and infinitesimal factor, which is the thickness of the abscissa. So it's okay. It's difficult, but it is okay. Historically, it is okay. Torricelli did like that, okay? Roberval, a guy I know quite well, he wrote this. In the same letter to Torricelli, it's more interesting. There is, however, I like that, a slight difference between Cavalieri's method and ours. I like in French, une petite différence. I like difference, and a petite différence for me, and for I think everybody in math, a petite différence, c'est ça. It's maybe, okay. The term a slight difference between Cavalieri's method and ours. The latter, in fact, considers the indivisibles of any surface according to an infinity of line, the indivisibles of any volume according to an infinity of surface, as if he wanted surfaces, to be really made up of lines, of volumes or surface. But so Cavalieri is not dumb, you know, he knows. It's stupid to think he really thinks that, you know. Okay? But our method, while not immune for reproach, at least avoids this one. Comparing heterogeneities, we consider our infinite or indivisibles as follows. We conceive that the line is composed as if they were made up of lines infinite or indefinite in number. The surface or surface, the solid of solids, and you read what is the following, the angle of angles, the indefinite numbers of indefinite numbers, and better still, the plane by plane of planes by plane, and so on. Indeed, each of these categories has its own property. I think it's a right, rich quotation, you know. But maybe we don't have time to comment that he consider the dimension of force, space, or object of force, dimension force, etc. Okay, generally it's interesting. But we see very clearly that he understands perfectly what is different between Cavalieri and he said it works the same way. Okay? That is for me interesting. Pascal would be maybe even more interesting to quote, showing the same, you know. Pascal, I wanted to make this warning to show, many quotations, to show that everything that is demonstrated by the true rules of indivisible, will also be demonstrated in the rigor and manner of the ancient. And that thus one of these methods differs from the other only in the manner of speaking, which cannot hurt reasonable people when they have once been warned or to what it means by it. The incomprehension in others comes only from their lack of intelligence, since nothing else it means but the sum of an indefinite number of rectangles made of each ordinate, which is of the small equal portion of the diameter. It's commenting a special problem for A, you know about that. And it is that is like abscess, it's the same thing. It works like. Are written made of each ordinate, not abscess, ordinate, which is each of the small equal portion of the diameter, the sum of which is certainly a plane, which differs from the space of the domicile only by a quantity less than non-given. We can recognize some dimension, you know, whatever it's it. But the advantage of the preceding result for determining the dimension of curvilinear space will not be missed by those who are even slightly versed in the theory of indivisibles. These points are familiar to those who have studied the indivisibles. And another quotation, Pascal said, of course, there is no problem to use this formula, the Cavalieri indivisible, on to speak of all the lines, because in many of these texts, it's all the lines. But, you know, we can see very clearly for him that the way it works in geometry is it's way of speaking. Okay, fine. Okay. And interesting, I made this comment. I did just with a few papers. Interesting remark about that. It's about Pascal. In Pierre Nicol's commentary in the preface to Logique or Art de Penser, la grande logique de Port-Royal, commenting on the prominence given to invisible in Pascal works and another Jansenist, Antoine Arnaud, one of the authors of the Grande Logique, the Jansenist theologian Pierre Nicole justified this method of indivisibles, method used by Pascal, a famous Jansenist, Arnaud, a famous Jansenist, and he said, very highly recommendable because it is incomprehensible. It's because of that, very, very rich. For this Jansenist procedure, the paradox is not a paradox at all, especially concerning the proud, very arrogant science that is geometry. It is God to discover the true things and results that our minds are not capable of understanding. It's a wonderful opportunity to recognize the smallness and insignificance of our own mind in the face of diving in nothing. That's excellent, you know. This aspect understandable and working well is very good, you know, because our intelligence, we are able to produce geometry, you know, quadrature or what you want, but understand, like God, no. Thanks to geometry. In Wallis, we can find, with different arguments, different styles, we see this thing. Look, whichever way we approach the question, either by an infinity of parallel line or by an infinity of parallelogram of the it amounts to the same thing. Consequently, in what follows, because this way of speaking, Pascal, seems to have proved his worth in Cavalieri method of indivisibles, partly also to ensure brevity, will sometimes call these infinitely small part lines rather than parallelograms. You know, or in Torricelli, I don't know if I have time to. It's a wonderful quotation, but it's, you know, it's the same, you know, from Torricelli, say, okay, it's work and I go to the end, you know. And the question is, for instance, I think it's a juicy position that in the great stage of building the algorithm of differential and integral calculus. The role, the status of indivisibles method is like in the beginning I told you, in the voie de garage, in the wrong way, you know. It's not consistent. And you know, so the question could be, is there exist a break or a continuity with the algorithm of differential and integral calculus? And for instance, also, I just mentioned in a few minutes that it is a very big dossier, you know, to Leibniz in mathematics, maybe in philosophy too. What about the links with indivisible method, you know? Are they present on continuity? Leibniz's arguments for the continuity of conceptions are numerous and clear, I think, clear and maybe different. Personages like Leibniz, you know, since Leibniz is not very great man, you know. He told that to UC in California, because in France, I think Leibniz is an imbecile, you know. But no, so I come. He pays a heartfelt tribute to Cavalieri and Torricelli, and then say, initiator and promoter who accomplished the precious task. And it is in the small text, Historia and Origo of Calculi Differentialis, a text written in this text in 1730. By chance, however, he speaks about himself. Leibniz speaking about himself. He came across Cavalieri's Geometria des Indivisibles. He consulted them for a while and liked the ease of the method used, but he had no courage at this time to penetrate his high mathematics. And then, referring to Kepler, Cavalieri, Fermat, Huygens, Wallis, Leibniz asked, who does not use the of infinitesimally small? But that is quotation we can do, but it's a book, maybe, you know, maybe it exists, one great mathematical book of Leibniz. It's a book who was lost, you know, and he was lost since 1676, when Cavalieri leave Paris back in Germany. And the manuscript was lost, you know. And it is a treatise, a big treatise, a quadratura, de quadratura arithmetica, circuli, ellipseus, et hyperbolae. And this text was completed in Switzerland, and it was beautifully reconstructed by Eberhard Knobloch. I don't know if you know Eberhard Knobloch. It's a very excellent historian of mathematics and specialist of Leibniz. And Eberhard Knobloch it's all the part of this treatise, and he published magnificent edition of that in 1993. It is an incomparable exposition, not only I say here, for the point, of continuity of the mixing of indivisibles method with integration algorithm due to Leibniz, who is all along this treatise, you know. We see very, very well concept, graphic, and, you know, idea, words coming from the indivisibles method context, you know, and to the, of course, the new calculus, the new concept, you know, the functional concept, if you take this, in Leibniz, you know. And it's a really wonderful tableau, spectacle of continuity, of mix of the two. The method, so there, Leibniz takes the method consisting in finding the order of certain figures by making sums of lines, otherwise known as the indivisible method, in the de quadratura. And having approached a curve with a gradiform surface, he concludes, this is what will make the indivisibles method and the use of gradiform space, so Leibniz concept, the sum of ordinates that are their prerogative, a rigorously demonstrated method and use. We speak about his method in the quadratura and to the last one. In Newton, it's more, I don't know, that way from Cavalieri than Leibniz, for instance, in Newton. We have a lot of common Newton on the question of the possible relationship and continuities between the ancient methods indivisibles on his own propositions. He explained, but he explained different things, and just quote one text in an important situation. In section 1 of the first book of the Principia, just after the 1 to 11, those things which have been demonstrated, all mathematical demonstrated of curved line on the superficies which they comprehend, maybe if they applied, to the curved superficies and contents of solids. These lemmas are premised to avoid the tediousness of reducing perspective demonstration ad absurdum, according to the method of the ancient geometers. For demonstrations are more contracted by the indivisibles methods, but so the indivisibles method, according to Newton, has effect, a good positive effect to reach more, the demonstration by the ancient method to make them, okay. But because the hypothesis of indivisibles seems someone harsh, and therefore the method is recognized less geometrical, I should rather to reduce the demonstration of the following proposition to the first and last terms and ratios or nations and evaluation quantities, that is, to the limits of those sums and ratios. And so to premise as short as I could the demonstration of those limits. For hereby the same things is performed by the indivisibles methods. And now, those principles being demonstrated, we may use them with more safety. So it's more, you have two sides of the, according the role of the indivisibles. Or not. So, I stop. Thank you.
There are two questions. Can you
Yes.
read?
Maybe for the question, I need your help.
Yes.
Yes.
It has. Of course, I applied the method of Mexico.
Close the method.
Okay.
Thank you very much.
Bogdan has two questions. He says, "Thank you for this superb presentation. I much appreciated it. Now, here is a question. In Euclid's proof of the Pythagorean theorem, for example, equivalent areas are used and moved as the proof needs. Is this possible that the method of indivisibles draws some inspiration from some older Greek sources?"
You know what I mentioned Euclid, it was not about, for example, the theorem de Pythagore. It's like a puzzle. You know, problem of infinity or very small. Or blah. It's not, no, it's mainly for the question of you know the surface exhaustion methods and that. So no, the question of use part of a figure on another, but maybe in the case of Marco. No, but no, it's not in question, I think. But the exhaustion method, one part of the exhaustion method is present in the element. That, or that, yes, it is. That's true.
See. And the second question is there any evidence that Cavalieri was aware of Erasmus' work, especially the Tractatus? Oresmes.
Cavalieri was est-ce que Cavalieri a lu Orem? Il était.
Good question. And I have the answer. The answer is we didn't know. We don't know.
We don't know.
We don't know. Or maybe an inquiry more precise could deliver the answer. But as I know, many also say, unfortunately, we don't know if Cavalieri really properly read directly Orem. So I can, maybe, but you know, on envie, we would not be surprised if we discover, because the Orem proposition is connected so near the concept of the use of indivisibles. Yeah, but we don't know. I don't know.
Bogdan says, merci beaucoup pour ces réponses. So thank you so much for this.
Thank you.
Other questions? Jose.
Yeah, but maybe I should draw a picture in the spirit of Cavalieri. So if Cavalieri's method, the omnes lines, so all the lines, were used to justify that this area and this area are the same, we could do it in this way. So here, you see, this is one, this is one. Let's start here. This line is equal to this line, and this line is equal to this line, and this line is equal to this line, and this line is equal to this. All the lines are equal. But obviously, this area is not the same as this area.
Yeah.
So here there would be a problem. And then Cavalieri would say, yes, but you are not using parallel lines.
Yeah.
And then my question is, what is important about parallel lines?
This is Torricelli point. This is exactly the Torricelli point.
No, but because.
And then what I think that is important is what Barrow and the other were mentioning is that actually it's not the lines that you're adding rectangles. Then when you add this rectangle with the next rectangle, there is going to be an overlap. Maybe it is infinitesimal, but there is going to be an overlap.
This is exactly the point of Torricelli. You are not really comparing lines, but you are comparing line with a obliquity.
Yeah.
It is obliquity relevant because it changes when you sum.
Yeah.
And so the indivisible of Cavalieri as indivisible that are homogeneous or non-homogeneous, but have no obliquity. The obliquity of the indivisible Cavalieri over Torricelli have an obliquity, exactly because of this point.
Thank you.
You know, but probably Cavalieri was aware about this difficulty. For instance, he produced ouais, mais j'ai là voilà, voilà, ici. Voilà. And that, yes, okay, I can do that. Like that, okay. Yeah, I'm gonna. No, only yes, we can say that. But he said, oh, we have to be careful because with this line indivisible on this one, and this one, we can conclude that the area of this one is the same as this one. And because of in the definition of the first method or second method, it's very important that the figure different is necessary. The indivisibles were produced were the same age, you know.
At same height, yeah.
Yeah, and in that's true. So that he can use in his circles to produce inequality or equality. Discuss about this on the chrome. But he used it just to produce a concept of all the circles. And he said that all the circle is proportional with the square of the rayon. And that's true that with the indivisibles in homogeneous quantity, we have no more to insist about this question of same
height.
I have also a question. That's something that I really never understood. It is a controversy about homogeneous and non-homogeneous. I mean, the controversy is a real historical fact, so I don't want to deny that it existed. But it seems to me that the obvious reply to it is Cavalieri's second method, that according to me is in no way a second method, is simply the first method explained in another way. So what Cavalieri seems to say in the second method is that's really not a problem where it's homogeneous and non-homogeneous. Why? Because what we consider as ratios, not sums. That is the real point of the question. So what is relevant here is not we to take all the line together. So what is relevant are the functional relation between the component or what we find in the figure. And this is the point. And so it seems to me that the reason for which all these people discuss and arrive to the same result, use the same language, but disagree on the interpretation, homogeneous or dishomogeneous, is simply because the method is the same, because what is relevant are not the sum, but the relations. And when you consider that, the fact that you are taking the ratio between epsilon A plus epsilon B plus epsilon C and epsilon A plus epsilon, there is epsilon not, it's not relevant because the epsilon goes away. because what is relevant is the rate that you consider. So I think that Cavalieri, with the second method, is not giving another method. He simply said, look, what is relevant is that, not the other point.
I agree with you. For me, all the literature about the poor methods, for me, are poor. I agree. But probably, in Cavalieri's, why probably he liked his first definition is, heterogeneous, because there is no inexactitude. When you produce your indivisible small rectangles, of course, you have, in particular in the curve, you have inexactitude, it's a question of inexactitude. And that is probably, he doesn't want that, he doesn't like that. Okay. But in fact, I agree with you. The way it works, it's the same.
The problem of this interpretation is exactly what's that problem? That this perfectly work when you have parallelism, and so where the component or are all ordered in the same way. When they order in different ways, so it appears that there is an essential difference between the homogeneity and dishomogeneity. But in fact, the point is Cavalieri only consider cases in which they are ordered in the same way. And it is Torricelli, the first one, that look, okay, now look in the other way. But then, when you consider the method not in the same order, then the question becomes much more delicate. And so the difference between homogeneous and non-homogeneous becomes relevant.
Excuse me.
Is
Is it possible to have
this back? Yes.
Because I have just not to continue the discourse. It is just I have 3 or 4 slides more, just the figure of indivisibles.
Okay. Figures.
Just to. Okay, for instance, this one, just to see how beautiful it is. That is Pascal. This one is Pascal one, and this is a figure. Copy from Descartes' demonstration. That is exactly the Descartes demonstration, and in line, it's heterogeneous. To square the sequoia. I have not time to explain it, but for him, for instance, of course, it's not. No, I am wrong. No, I am wrong. It's more complicated, because Descartes. The Descartes seems like that, but Descartes, it is a triangle here, and then he has to work with this part. That is Roberval. It's Roberval, but the people, I don't know where I found this picture, but it's a mixed. It's interesting because Roberval was really, maybe we have a figure. Look, it's this one that I try to show it. That is nice too. That is Roberval too. Well, anyway, I come back to this one. Yeah, that is Roberval idea. It's the first time in the history of geometry that we have the sinusoidal curve here, and then he shows that this part is equal to have the more interesting argument. The point is, the people who produce this figure produce the Roberval argument. But in Roberval, of course, it is with homogeneous. So we don't have, it's like, I don't know where it comes from. But the figure is nice. What else? Maybe, so this is, and that is Descartes. That is Descartes. Yeah. I know. That is Descartes. And this one is a Torricelli one, approximation. You know, the point with Torricelli, we are not far, just point of view of the future, with une somme d'intégration.
Integral sums?
Oui, the figures. And look at this one too. It's interesting because it is a comparison in two figures. You have this one and this one complete, and this one. Compare with one of the figures little triangle as indivisibles, and the other parallelogram. Each of one are in the ratio double, to show that the surface here is twice of this one. You know? And it's it's Roberval. And Leibniz used exactly the same in this three times. Oh. Okay. Roberval. Like we have other general situation now. For instance, that is a concrete, and the point is to produce a small indivisible like here, compare and added with to compare with the area of the big circle or the area of the second one. So it's a word that produces all the results, geometrical results produced by indivisibles method. Oh. Oh.
I have another question. You said in the beginning, very beginning, that in the latitudo formarum, there is the idea that the intensity can be compared, can be considered equal, but they cannot be added one to the other.
Yeah.
Okay, but this is true historically. This is not done. So I am not contesting this fact. It is an historical fact. But
and not only historical. How can you add some the speed?
But okay. But my point is the following. If you have Saint-Anselme virtue,
Yeah,
okay,
that's a good example.
you have this case. This is in any moment, in any instant, any day, if you want, the virtue of Saint-Anselme, and so the totality is the area. And then you have the virtue of Saint Thomas.
Yeah.
The virtue of Saint Thomas you can perfectly put here, but why not put here the virtue of Saint Thomas? Here, and then you have this, and then this area is the sum of the virtue of Saint Thomas and Saint Anselme. Why not? Possibly, from a modern point of view, we can take that the problem is that it was a problem, because this has not the same obliquity.
No,
but this seems to be very strange.
No, because it would be still...
Yes, but the parallel here is here, and this would be something else, because the area is not parallel. So, but I think that I refuse to think that Torricelli was thinking that this was the problem. So why nobody does that? Why nobody does that?
What did you obtain?
Why nobody sum the virtue of Saint Thomas and
what do you obtain?
I obtain the sum of virtues
Of Thomas de Anselmo?
Oh, yes. No, I say, okay, we have the virtues of Saint Anselme, and then the virtue of Saint Thomas, and then I have the virtues of both of them. Of course, we can sum the virtue of the sun. We never arrive to the virtues of God. But put together the virtues of
all saints and all angels.
there are. So,
Angels
in
don't
that,
have-
why not? So an explanation could be that we have no physical fact that correspond to that. And so the mathematics here would be farther to the reality. Because if I sum, for example, the red of teeth and the red of teeth, I have not more red. So there is a physical fact that forbids this idea. But mathematically speaking, that is possible. So you think that there is a empirical idea that forbids that is mathematical development. Mathematically, I know why.
If you have one area and another one, you can sum that.
Yes, that's my point. By the way, in many cases, I have the speed of a car on a road that, or the speed of a car on a ship. So there is the sum of the two speeds. So in many cases, it's work, physically speaking. So I have two speeds that sum one to the other, and that is work. But why it is? I never see it in the rest. Never seen it in the Mertonia.
You know,
There were no cars at that time.
Possibly. No, but this is a historical question that I always
I see,
had. Why there is no
Well,
something like that?
when was it Abraham is discussing with the angel of God whether they are going to destroy or not Sodom and Gomorrah. I don't know the names in English. The two cities. There is a Sorites right there, and then God said, "I will destroy them," and Abraham said, "But what if there are 50 virtuous people?" Say, "Okay, if there are 50, I'm not going to destroy them." Okay, but what if there are only 40? Say, "Okay, if there are 40." So the joint virtue of all those people would save, but only the virtue of only one of them is not. So the
But
virtue of
this
people
is
can be
interesting
added.
because when Newton, much later, with argues, starting from Wallis method, that the integration is linear, make exactly this reason.
and maybe it's a,
So why not? Why we need a Newton to do that? That's I do not understand.
Marco, maybe one thing.
Sorry?
It's difficult.
It's difficult.
Yes.
Why?
Because you just proved it. You needed Newton.
But they seem to me.
But so when all those people are speaking about adding rectangles, this is essentially what we call nowadays Riemann sums.
Yeah.
So what is attributed to Riemann? What is that he did that it deserves the name Riemann sums and not Torricelli sums?
No, but you are right because when I saw the figures, you know, for instance, the Torricelli's book, it's Riemann, you know, the drawing are exactly the same, you know.
No.
And of course, in Leibniz, in the famous book I was talking about, yeah, when he talk, I pronounce the term, surfacing curve or something like that, the area, it's exactly the same. We have curve and we have small parallelogram, but we know that like Descartes said, a partie dépassante, it's a small part, you know. The sum of this party could be less than epsilon. You know, okay, it's possible. If I do that, okay.
But,
I remember when I was a scholar in the high school, same thing.
The idea of Riemann is exactly the idea of Torricelli.
Yes.
This is clear. What Riemann
Yes.
more, Riemann first is generalizing, but the second idea is to make it rigorous because instead of considering an approximation
That's what he
on
did.
one side, he considers two approximations, and then he put a condition that the info one is equal to the sub of the other, and this is possible. Sometimes it happens, sometimes it does not happen.
But isn't
And he said that the cube is integrable only if the inf is equal to the sub.
Is-
This is something much more
Isn't
But
it
the
same-
basic idea,
isn't it
what
not
is
the
the
same as-
Roman, is simply to say, okay, now I try to make rigorous the idea of Torricelli.
But this is exhaustion and Cavalieri's or together, no?
Sorry?
Is the method of exhaustion exhaustion and and Cavalieri's together.
Absolutely, yes.
But he added the rigor to it.
And probably
But in the end of the story, no.
the existence of
But this is not
function.
the famous idea of epsilon delta that is very often presented as a great revolution introduced by Riemann and Weierstrass.
Yes.
And the method is perfectly clear in Euclid when he say that what is relevant is that we can go as far as in the proposition first proposition book 10 is to say exactly that. If you have a certain magnitude, I don't remember if it's first book 10 or book 11. It's 111, I think, not 110. It's not so important. I think that the proposition 1 of book 11 says, if you have a magnitude, whatever it be, and for this magnitude, you eliminate more than an half, and then you eliminate what remain more than an half, and that you eliminate more than, you can get as far as close as you want to the original. It does not go, you go infinitesimally forward. But
As much as you want.
as close as you want. That is, for any small difference, you can protract the sum as so far such a way that the difference. This is absolutely clear in Euclid. So this is,
But it's not the way.
it takes 2,000 years to arrive to Weierstrass when the idea is already there. Why? Because there is in Euclid there is that, but there's no the idea of function. There is no language to explain that epsilon, that delta is a function of epsilon. There's an idea, this functional language is not there. Once Weyer starts the functional language, then it becomes obvious to explain the solution.
I see.
And this is the same for Riemann. Riemann has the language. Torricelli and Cavalieri have not.
And it is really impressive to compare
That is
the
true.
Riemann figure.
Riemann is making
and
the method
Torricelli.
indivisible. Absolutely. Other questions? Remark, objection, protestation?
No.
So,
Thank you.
So, there's a super.
there is. Okay, go then.
Sorry, yeah. There's
A protestation, finally. A student a protest.
yeah, I was shouting down the applause.
Okay.
No, there's a super popular math book. It's not an academic text. It's like a pop math book on the history of calculus. It's called Infinitesimal. And in it, and because I haven't read Cavalieri's work myself, it's claimed that he avoided proving new results using his method, so as to avoid controversy due to the contentious nature of indivisibles. And I know that that's not true for he has quadrature formulas that were novel, but I'm just wondering if maybe there's specifically in the Geometria Indivisibilia text, if it's the volume formulas in there are all well established, and he just wants to demonstrate the efficacy of his method. Is that, but I don't even, so I'm basically fact checking this pop math book, and I'm wondering if you can help me.
Okay.
Yeah.
So if I understand well, the point of James is that Cavalieri does not apply. Sorry. Si j'understand, si j'ai bien compris, son point est que Cavalieri, il n'applique pas sa méthode pour trouver des résultats nouveaux, mais simplement pour retrouver d'une autre manière des vieux résultats. Et en quelque sorte, le fait que les résultats qu'il retrouve sont justes, justifie a posteriori l'usage de cette méthode. En quelque sorte, il justifie sa méthode en disant, regardez, en utilisant ma méthode, je retrouve les mêmes résultats qu'on a déjà retrouvés avec la méthode des anciens. Et il veut,
C'est vrai, it's true that Cavalieri explanation that within Cavalieri, we can see the most important for him is to say it's working well, more easier, more, better, and it proves that it's working well.
Yeah.
That's all the ancient result of it. That's true. Maybe we can, reading Cavalieri, we could think, oh, the most important for him is to produce something more easy, we can play, we can.
Something deeper
It's
than traditional methods.
it's a new method, but look at what he. But in fact, thanks to him and others, we have a lot of new results.
Yes, if you in the hands of Torricelli and in the hand of Wallis, the method produced
That's
very
true.
new results.
But look at
It's just
how.
things like such, he could have,
Very
I'm sure
good.
he knew he could have calculated a lot of new volumes.
Look
He
at
just chose
how we
not
talk
to.
about the foundation of the nature, the very nature of his object, absurd, ununderstandable, so contradictory. He things very strong.
Yeah. I think he was worried people wouldn't believe
But there is
believe his new results.
sorry.
People wouldn't believe his new results unless he used the method to verify old results.
I don't know. Do you know something about that? No, but I quote a lot of some people telling it works very well. It's wonderful, including for instance.
As far as I know, there is no objection to
Yeah.
the result.
To the result, no, I don't think. So. For
Torricelli and
instance,
Wallis.
Gildin, very enemy of everybody, he didn't produce false results. I don't know. Maybe.
But even when Wallis, using this method a little bit modified, arrives to the conclusion of an argument not really proved because the method is not very rigorous, that the circle cannot be squared. This is a fantastic result. But starting from this moment, nobody still believes that you will square the circle. So the result of Wallis is accepted by anyone, even if the argument accepted by anyone, up to the point that in the middle, 50 years later, Wallis, the Academy of Science in Paris, decided not to read any other memoir where someone suggested that we can scale the circle. So the community accepted the result of Wallis unanimously. What is not the same to accept the method of Wallis. Method of Wallis is discussed a lot, but the result, it appears obvious, acceptable. So, and there is no a lot of example of error produced by the method of indivisible. I don't know. There are, but I don't know.
They are difficult.
I don't know.
No, because they had maybe some difficulties with
No, there is an
comparing
there is an error by Wallis. There is an error by the quadrature of the spiral.
because
the quadrature of the spiral.
indivisibles are not the same form.
Yeah.
For instance,
Yeah, yes, that is true. The argument, the result on the spiral is wrong.
in the case of Roberval's result, I produced no.
Okay, thank you.